Picture a stretched rubber sheet. I drop a heavy marble in the middle, and suddenly every other marble starts curving toward it. That's the classic gravity demo, not just a party trick. Mass tells space how to curve. Curved space tells objects how to move. Now here's the hook. De dreht spoor en dauer en zee en drooier jur en dauer. Drain the dip. In that sheet is a gravity well. The heavier the mass, the deeper the well. The deeper the well, the more energy you need to climb out. Imagine placing a small marble near that heavy one. If I flick it gently, it spirals in. Flick it harder, it loops around. Hit it with enough speed, it escapes the dip, barely. That enough speed is escape velocity. Planets make their own wells. Earth's is decent. Getting to space takes about 11.2 kilometers per second. Mars, its gravity well is shallower, so escaping is easier. Jupiter, deep, steep, unforgiving. The point stands, deeper well, more thrust, more fuel, more engineering. Black holes push this to the limit. Pack enough mass into a tiny region and not even light can claw its way out. That boundary, the event horizon, is the place where every possible path curves inward. There's no fast enough from there. But here's a twist. Objects in orbit aren't fighting the well head-on. They're falling around it, constantly missing the center. Orbit is the art of sideways speed. That's why rockets don't just go straight up. They pitch over to build horizontal velocity, trading height for a stable path through curved space. The rubber sheet is a 2D shadow of a 4D story. Space and time bend together. Energy, mass, motion, even light's momentum plays a role. The sheet can't show time, but it nails the intuition. Curvature changes the rules for every traveler. So next time you see a marble swirl into a dip, think fuel budgets, escape plans, and black holes. In a curved universe, the shortest path isn't always straight, and climbing out takes work.
Hello world. Today we're going to talk about the geodesic curvature. In this version, the geodesic curvature that describes gravity is illustrated in a new formula. Darkness is filled with node particles. Space is not empty as some explain it to be. I understand this idea I have developed as the filler for freefall. A mesh of these particles directed under the planet's density field, not as a wave, but particle behavior. Even in the darkness of zero vacuum space, these particles assume their responsibility.
Picture space-time like a giant rubber sheet. Far from anything massive, it's flat. Drop a star on it, and you get a cozy dent. Give a marble a nudge, and it orbits the dent. That's the classic Einstein analogy. Simple, punchy, memorable. But here's the catch. It's only an analogy. Real gravity bends space and time together, not just a stretchy sheet. A marble on rubber doesn't move exactly like planets in space-time. Now, about the universe expanding. Today's best direct measurement puts the Hubble constant around 73.5 kilometers per second per megaparsec, about 45-46 miles per second per megaparsec. Key phrase, per megaparsec. That's a rate, not one speed for everything. Farther galaxies recede faster because space between us stretches. Some can even recede faster than light, and that's fine, because it's space expanding, not objects zooming locally past light speed. This is where Hubble tension kicks in. Measurements of the nearby universe and predictions from the early universe don't agree. One says faster, one says slower. That mismatch hints at new physics. Or a sneaky systematic error we haven't nailed yet. Enter Kawecki's 2026 idea. He claims a 2-to-1 ratio that straightens gravity wells. He says space expands near twice light speed, driving orbits, rotations. It's a bold pitch, but it's not peer-reviewed or accepted by mainstream physics, and mixing up per megaparsec with a single universal speed leads to confusion. So here's the clean takeaway. Einstein's space-time curves guide how matter moves. The universe's expansion is real and weird, possibly accelerating thanks to something we call dark energy. Recession can outrun light at huge distances without breaking relativity. And new ideas? Bring them. Just test them hard. If the rubber sheet got you curious, you're already doing physics right. Ask better questions, then measure.
What is the fabric of space? Not the textbook version. Let's try a weird thought experiment. What if space is a smooth, massless liquid like a cosmic oil spreading everywhere? If space is a liquid, then gravity is what happens at the surface. Picture a vast, invisible grid that behaves like a stretchy film. Put a planet on it, and the film dents. Things slide toward the dent. That's gravity. Classic. But here's the twist. The universe isn't just sitting there. It's expanding. And that expansion can outrun light. Not by moving stuff through space faster than light, but by making more space between stuff. If space is a liquid, it's like new oil is constantly bubbling up, making the surface spread. So where does dark matter fit? In normal physics, dark matter pulls. It adds extra gravity. In this fluid picture, think of it as hidden thickness in the liquid, an unseen weight that deepens the dents without glowing. More thickness, deeper wells, tighter orbits. Now, imagine planets as leak points. On a world's surface, oil might seep up from underground, pushing outward as it rises. Translate that to space. A planet bends the grid downward, but there's also a gentle, repulsive expanse swelling from beneath. Fresh space filtering up through the fabric. The result looks like an open gravity well that's constantly being nudged flatter by expansion. That makes planets feel stuck, caught in bubbly, broken patches of the liquid surface. They don't fall through, they bob and settle where the dents and the upwelling balance out. Across the cosmos, new space flourishes. The grid stretches, voids widen, galaxies drift apart. The fabric curves where mass is and smooths where expansion swells. Let's give this picture a name: Kawecki Expanse Gravity. In this story, heavy bodies act like ground leaks for more space, feeding the surface while holding their wells. The universe obeys an expanding rhythm, say a 2-to-1 ratio, where the swell races roughly twice as fast as light spreads information. That doesn't break the rule. The limit is for signals in space, not for space itself. So, is this how the universe really works? Not necessarily. It's a thought experiment. But it helps me ask sharp questions. If space behaves like a liquid, what sets its viscosity, its resistance to being bent? Could dark matter be the hidden thickness that deepens wells? And is dark energy just the pressure of new space filtering up, everywhere, all at once? Maybe the cosmos is a calm surface with endless bubbles underneath. We feel the dents, we see the stretch, and between them, reality flows.